Okay, 8.2, distribution of the sample proportion. Point estimate of a population proportion. Suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic, right? So think about when we did the binomial probabilities, success or failure. The sample proportion, which is denoted p hat, is given by this formula, where X is the number of individuals in the sample with the specified characteristic. Okay, the sample proportion p hat is a statistic that estimates the population proportion p. Okay, so the population proportion p is really a different statistic than the population mean, mu, but for the sake of this course, really, and they're very close if not the same thing. So for the sake of this course, if you want to have it in your mind that that's the same thing as mu, that's fine. Technically, they're a little bit different. This is a population proportion, right? And mu is the population average. Okay, let's see what we have here. In a Quinnipiac University poll conducted in May 2008, 1,745 registered voters nationwide were asked whether they approved of the way George W. Bush is handling the economy. 349 responded yes. So obtain a point estimate, okay, p hat, point estimate, for the proportion of registered voters who approve of the way George W. Bush is handling the economy. So our point estimate of the economy is simply X, 349, over N, 1,745. That's all it is, right? The point estimate of the proportion, 349 divided by 1745, so 0.2. 0.2. So if we did a second survey of 1,745 voters, we would likely get a different estimate of the proportion because different individuals would be in the sample. Because the value of p hat varies from sample to sample, it is a random variable and has a probability distribution. So to get a sense of the shape, center, and spread of the sampling distribution of p hat, we could repeat the exercise of obtaining simple random samples over and over and get us a list of sample proportions, right? Just like we talked about last time in getting the list of those sample means. So same thing, right? Same thing. Different parameter though. Okay, so they're saying they used a simulation to get these. We're not going to do simulations, but by whatever method we get the histograms is fine. According to a Time poll conducted in June of 2008, 42% of registered voters believe that gay and lesbian couples should be allowed to marry. So it says, describe the sampling distribution of the sample proportion for samples of size 10, 50, and 100. So here we are, N is 10, N is 50, N is 100. So describe the distribution. Okay, so first, remember, describing a distribution means we're going to talk about its shape, its mean, its standard deviation. So if I tried to draw through all of these bars, I might say that shape is skewed right. Okay, skewed right. This one, okay, is more normal than this one. It's got this wonky thing here. we might say approximately normal. Okay, this one, okay, much closer to normal. Okay, they've calculated the mean and the standard deviation for each one. And look, the mean of this one is 0.426. The mean of this one, 0.426. The mean of this one, 0.42. Look what P was. So basically, these means are the same. Standard deviation of this one, 0.16, 0.07, 0.04. So the standard deviation got smaller and smaller. So they're not as dispersed. The data is not as spread out. Okay. I think the next slide, I was about to say something, but I think it's already on the next slide. Yes, the key points regarding the sample distribution of the sample proportion. Shape. As the size of our sample increases, the shape becomes approximately normal, right? Gets more and more normal. The mean of the sampling distribution of the sample proportion equals the population proportion P. So the mean is equal to P. The spread, the standard deviation of the sample proportion decreases as the sample size increases. Okay, same key points we had from last time. Remember when we were talking about the mean distribution, the sample mean distribution. Okay, for a simple random sample of size n with a population proportion p, the shape of the sampling distribution of p hat is approximately normal under these conditions. Okay? Remember we had a condition last time for it to be approximately normal. That was for n to be greater than 30. Okay, the mean, now we've got this condition for our population proportion. The mean is the same, so the mean of p hat is p, and the standard deviation is this formula right here. Okay? So the model on the previous slide requires that the sampled values are independent. Okay? And when sampling from finite populations, this assumption is verified by checking that the sample size is no more than 5% of the population, right? The sample size has to be less than 5% of the entire population. Okay, that's because the success or failure of identifying an individual in the population that has the specified characteristics should not be affected by earlier observations. Okay, it's got to be independent. For example, in a population of 100, where 14 of the individuals have brown hair, the probability that a randomly selected individual has brown hair is 14 out of 100. The probability that a second randomly selected individual has brown hair is 13 out of 99. Okay? This probability changes because we didn't do replacement. So we got to have a population size that indicates we're independent. Now, regardless of whether or not this condition is met to make it approximately normal, the mean is still P, the mean P hat, and the standard deviation is still this formula, okay, whether it's normal or not. Okay, according to a time poll conducted in June of 2008, 42% of registered voters believed that gay and lesbian couples should be allowed to marry. Suppose that we obtain a simple random sample of 50 voters and determine which voters believe that gay and lesbian couples should be allowed to marry. Describe the sampling distribution of the sample proportion for registered voters who believe that gay and lesbian couples should be allowed to marry. Before I can describe that, I got to see if it's normal or not. Okay, so first of all, I'm going to check my size. Well, this is, who are we? Registered voters. Okay, and our sample size is not 90, it's 50. Our sample size, come on, pen, is 50. I just made this PowerPoint, and the next one I think is 90. The sample size is 50. We're talking about registered voters. So I don't really have a total number of registered voters, but I know that's less than 5% of them, right? 50 people is nowhere near 5% of the registered voters. Okay, so that checks out. Okay, then I have to say N times P, 0.42, times N minus P, so 0.58. You know, you can put it on your calculator if you want. I got to make sure that's greater than 10. 50 times 0.42 times 0.58 is 12.18. Okay, so now I can describe it. I know that it's normal, approximately normal. I know that the mean of P hat is P, 0.42, and I know that the standard deviation of P hat is P times 1 minus P over N. So plugging that in our calculator, we get 0.0697, 0.0698, rounding appropriately. Okay? Okay, now that we can describe the sampling distribution of the sample proportion, we can compute probabilities involving it, right? So, according to the Centers of Disease Control and Prevention, 18.8% of school-age children, ages 6 to 11, were overweight. First thing I want to do, let's see, yeah, here's where our N is 90. N is 90. We're talking about school-age children, and so I don't really know how many children that are, but once again, I know 90 is way more than 5% of all school-age children. Now, let's do N times P times 1 minus P and make sure it's over 10. 90 times 0.19 times 0.81 is 13.851. Okay, so now I know that the mean sub P hat, mu sub P hat, is 0.188, and I can find sigma, right? I'll write it up here just so maybe we can see it. So it would be the square root of 0.188 times, let's see, 1 minus 0.188 is 0.812, all over in 90. Okay, let's put that in our calculator. Square root of 0.188 times 0.812 divided by 90 is 0.0412. Okay, so now this says, in a random sample of 90 school-age children ages 6 to 11 years, what's the probability that at least 19% are overweight? So at least 19% means 19% or more. That's the least. So the first thing I'm going to do, and I'll do this one using the chart, and then we'll do another example using our calculator, right? We want to be fluid at both of them. Okay, so let's convert that to a z-score. So we've got 0.19, remember? 0.19 minus the mean over the standard deviation to get our z value of 0.0412. Okay, 0.05. I got 0.048, but 0.05 because we rounded two places when we're looking on our z chart. Okay, so if I'm going to look on my z chart at 0.05, okay, I get 0.5199. Okay, so that tells me that the probability that z is less than or equal to 0.05 is 0.5199. Okay, but remember what our chart tells us. Okay, it always tells us, so 0.05, this is 0, this is 1, so it's giving us this number. We want at least, so we want this number, more than this, so we've got to do 1 minus 0.5199. Okay, 0.4801. All right. So the probability that at least 19% are overweight in this sample of 90 school-age children from 6 to 11 is like 48%, 0.4801. Okay? Suppose a random sample of 90 school-age children from 6 to 11 results in 24 overweight children. What might you conclude? Okay, this time, notice what it gave us. It gave us a number instead of the percentage. So the first thing I have to do is figure out what my point estimate is, my p-hat, in other words. Okay, up here, it gave me it. But 24 over 90, if 24 out of the 90 are overweight, then that's 0.2667. So 26 2/3%, 26.67%. Okay, so then I just do the same thing. Find my z-score for that. Minus the mean. Divide by the standard deviation. And we find out that that is 0.2667 divided by 0.188, not divided by 0.2667, clear, 0.2667 minus 0.188 divided by 0.0412. Okay, and so I get 1.91. So then when I look on my chart for 1.91, 1.91, I get 0.09, not 0.09, sorry guys, 0.9719. 0.9719. Okay, but let's see if that's our probability or we need to use the complement, right? So, suppose a random sample results in 24 overweight children. Okay, so this is the probability that less than 24 are overweight, right? Nearly always less than 24. So we want to know 24 or more, technically. So we need to use the complement again. .0281. So that should happen about 3% of the time, right? That means out of 100 kids, you should only expect to see 3 of them overweight. So in this sample of 90, less than 100, and you had 24 overweight, that's very unusual to say the least. So what might you conclude? You might conclude that that's not really the correct mean, right? That the mean of overweight children is higher than that. Okay, let's do one more example. According to creditcard.com, 29% of adults do not own a credit card. Suppose a random sample of 500 adults is asked, do you own a credit card? Describe, once again it's just saying describe the sampling distribution of p hat, the proportion of adults who do not own a credit card. All right, so to describe it, first I need to know if it's normal or not. All right, so 500 adults. Do you think that's less than 5% of adults that do not own a credit card? Okay, I'm going to have to assume that it is. Okay, well, none of these examples, they gave us an actual number. Let's say we know that there's 2 million people that don't own a credit card. Okay, and there's way more than that. So what would I do? I would say 5% of 2 million. Okay, just as an example to see how we would do this if 1, 2, 3, 4, 1, 2, 3, 4, make sure I get the right number of zeros. Okay, so that is 100,000 people. So think about that. Is 500 less than 100,000? Oh yeah. Yeah, that's what I'm saying. On these sample examples that they're giving us, we don't really have to worry about that being less than 5%. It should be obvious that, oh yeah, that's way less than 5%. Okay? But if you're given, you know, let's say your population is the students at Weatherford College and they tell you, you know, there's 5,500 students, then you can figure out, okay, what's my number there? What's my break off number? Okay, so this is less than 5%. Now I've got to do N times P times 1 minus P and see if that's more than 10. And that is 102.95, so yes. All right, that means that we know that mu sub hat is 0.29 and sigma sub p hat is, okay, the square root. So let's just put this in our calculator. I'll write it down here and then we can erase it. Okay, the square root of p times 1 minus p over n, right? That's our formula. .0203. Okay. All right, this one just said describe the sampling distribution. So we know it's normal because these two conditions met. Well, this is less than 5% and this is more than 10, so it's normal. And we know the mean, mu sub p hat, is 0.29 and the standard deviation is 0.0203. What is the probability that in a random sample of 500 adults, more than 30 more than 30% do not own a credit card? Okay, so once again, let's think about this, right? And if I'm going to do my calculator this time, I don't need to change to a z-score, so I'm going to say that my mean is 0.29, right? And one standard deviation is 0.3103. Okay, so 0.31. Okay, so 0.3, more than 0.3. That would be about right here. Remember, our calculator, just like the chart, is going to give us this number. And it's asking about this value. Okay. So remember to go to second Bayes to get into your distribution. Choose your normal cumulative, CDF. Okay. And our calculator is going to be based on this. So we're going to say 0 or lower bound all the way up to 0.3. Put in your mean, 0.29, and your standard deviation, 0.0203, and see what that is. Okay, let me get there. Okay, 0.6889. But remember, that's this value. So the probability that x is greater than or equal to 30% is 1 minus 0.6889. So 0.3111. Okay, about 31% probability that more than 30% of the people in this sample do not own a credit card. Okay, what's the probability that in a random sample of 500 adults, between 25 and 30%? So it's the same thing. Except we've got a lower bound this time. So put 0.25. So I can just hit second enter. Well, I'm going to do it twice because I did this in my calculator too, but if I hit second enter, I don't have to go in and re-enter the whole thing and go to second vars. However is more comfortable for you. All I've got to do now is go in and change that 0 to 0.25 because look, everything else is the same. So I just want to change that to 0.25. So the second delete will insert, and you can put 0.25 in there, right? And so that is 0.6645. And this is our actual answer because that did give me, so this one is giving me the value, so let's say 0.25 is here. So that does give me this, which is what I wanted. Right? Instead of 0 all the way up to 0.3, this value gave me 0.25 up to 0.3. Would it be unusual for a random sample of 500 adults to result in 125 or fewer who do not own a credit card, and why? Okay, same thing like on that last one. Instead of giving me the actual percentage, right, instead of giving me my P, my proportion, I've got to find the proportion, which is just 125 out of 500. Oh, that's a fourth, right? So 0.25, 125 out of 500. And then, same thing, normal CDF, and this is, I'm going to switch to green so we can do this. Okay, 125 or fewer, okay, or fewer. So this one, my calculator is going to give me what it's asking for. Okay, so we're going to put in 0 again to 0.25, 0.29, 0.0203. Okay, so I'm going to hit second enter again, and I'm just going to change those first two entries to 0, comma 0.25. Get rid of that extra 3 that left. Okay, 0.0244. Okay, so now actually this question didn't ask me to calculate the probability like this. What's the probability? What's the probability? This one said, would it be unusual? But to answer that question, well, I needed to know, well, I don't know, what's the likelihood, the probability of that happening? And so, oh, the probability of that happening is like 2%. So would that be unusual? Yes, that's unusual. Why? Well, because the probability is only 2% of that happening, right? And if we need more explanation, we can say, and that's less than our 5% rule of thumb. Okay, that's chapter 8. Let me know if you need anything.